Greetings everyone. Today we'll talk about cylindrical coordinates. Now just like any other coordinates in three-dimensional systems, we'll need three different numbers to identify a point in cylindrical coordinates. We call these numbers r, theta and z. Now cylindrical coordinates are really a combination of polar coordinates for the xy plane and having the z coordinate attached along with the polar coordinates. So you'll see some similarities right now. Now if we go from Cartesian coordinates to cylindrical coordinates, we use the exact same transformation rules in the xy plane as the polar coordinates. So our r squared equal to x squared plus y squared, as you'd seen polar coordinates, and tan of theta is just y over x. Z doesn't change, so we have z equals z. And similarly, we can go from cylindrical coordinates to Cartesian coordinates. In the xy plane, we have the same rules as for polar coordinates. X equals r cos theta and y equals r sin theta. And z doesn't change, so z is still z. Now let's see how to plot a particular point in the cylindrical coordinate system. So let's here we have r equals 2 and theta equals 2 pi over 3 and z equals 1. So let's first draw out the xy plane, like how to move across the xy plane in the cylindrical system. So first we note that our angle is starting from the positive direction in the x-axis, which is here. We go 2 pi over 3 radians. So this is pi over 2. A little over that is 2 pi over 3. So it's it's somewhere along here. So this is along the xy plane. So it has no height. It has a z value of this particular line has z value of 0. And we go this distance exactly 2 units, because r equals to 2 from the origin along the xy plane, and now we will move 1 units vertically upwards. Because our z value is 1. So this particular point over here is really the coordinate that our question asked, which is 2 pi over 3 and 1. So here you can also see this. The book drew it like this, like it's the same diagram. So you go over 2 pi over 3 angles along the xy plane, move 2 units from the origin, and then just move 1 unit upwards. Then here we arrive at our desired coordinate. Now, as I have mentioned before, the cylindrical coordinate is just a combination or a blend of the polar coordinate and the Cartesian coordinate. Now, in the volume element in the Cartesian coordinate is, it's just let's say it's dz, dy, dx, or any other permutation of them. It's still the same thing, such as dx, dy, dz, or dy, dz, dx. It doesn't really matter. But here it will kind of help us if we write in this particular order, or dz as being the first one. And what we should note that dy dz is just the area element, or dA. So we can write this as dz dA. Now if you remember from week 5 materials, like in polar coordinates the area element is just dr dr d theta. Right? And if I now substitute this part over here for dA, we will get the volume element for our cylindrical coordinates, which will be nothing but r, and we have dz and just dr d theta. Now this is written in this particular way just to preserve the order, but you can write it in any way you want. It doesn't really matter. And this is an example of how we will define a particular solid in our to calculate a triple integral over a volume. We'll call this solid E. So E will have points x, y, and z, because this is all these points are in 3 dimensions, and x and y are on the xy plane. So, and x and y actually belong to this particular region called D, and our z is actually bounded by these 2 functions. The first one is u1 of x comma y, and then we have u2 of x comma y, and our d, the points in D can be labeled as, let's write this r theta, it's the same thing, so we got r and theta, and we can say that r is bounded between h1 of theta, that the distance from the origin is always greater than this particular function, and it's smaller than or equal to h2 of theta, and our angles are in between alpha and beta, so we have theta going over alpha and beta. Now this particular volume integral over, if we have any function that we want to integrate over, for instance f of x, y and z in Cartesian coordinates, if you want to do that, this is our triple integral over our domain E, or this entire solid we want to integrate over, and our function f x comma y comma z over the volume element dv. Now if I want to do this in the cylindrical system, what we have to do is simply write our limits down. So the first limit we will write down is our z, which is u1 x comma, instead of x we will write r cos theta, because x is r cos theta in cylindrical system, and y is r sin theta. Similarly, you will have u2 r cos theta, r sin theta, and we have our r function in between h1 of theta and h2 of theta. Finally, we have our last limit, our theta, which will be constants a and alpha and beta, and we now integrate the function f of x is r cos theta and y is r sin theta, and z is just z in cylindrical system. So now we will have r dz dr d theta, because our volume element in the cylindrical coordinate system is r dz dr d theta. Now that's how we evaluate triple integrals in cylindrical coordinate system. We'll see examples of how to do this as we move along. Now let's look at some geometric interpretation of the volume element. So now this is very similar to how we developed our geometric interpretation for the polar coordinates. So we have this particular solid, and this solid, when we consider the infinitesimal lengths along the r direction, we have dr, and z direction we have dz, and this particular side will have, in the same way that we had r d theta before, we will also have r d theta over here. Now as with the limits of calculus allow us to approximate this as nothing but a cuboid with the three sides r d theta, then we have dr and dz, just like dr and dz, and the volume of this particular cuboid is just the length, width and height. So we have let's we'll write this in the way so that our order is obvious. So we have dz dr d theta. It's just the product of these three things, now arranged in this way because we usually do the z integral first and then the r integral and the theta integral at the last. So this is just our volume, a geometric interpretation of the volume element in cylindrical coordinate system.